Okay, so we're now going to expand or generalize a little bit these skills we've had with linear regression, you know, the least squares method, drawing the line of best fit. And the idea is, in reality, there can be all sorts of relationships or different types of correlation between bivariate data. Sometimes it represents a line, sometimes it could be a curve, right? Just because it's not a line doesn't mean there's not a relationship. So the idea is we're going to be looking at different ways in which bivariate data could have a relationship. But then how do we prove it? How do I prove that you know, a set of data follows, say, an x squared curve rather than just looking roughly like it? And how do I know it's x squared? How do I know it's not x cubed? So that's what we're going to be looking at, and these are called exponential models. We'll see why they're called that if it's not obvious already. But before we do that, just a quick check. And this is, you know, sort of pure maths question, but it completely relates to what we're going to be looking at. Can you identify, using your intuition, about how powers operate? You've got there 4 graphs with 4 different colours. Can you match the colour of the graph to the 4 equations? Which one is which? Give it a go. Okay, and as it turns out, the purple one, that's x squared. Red one's x cubed. Perhaps the trickier one is 2 to the x and 3 to the x, which are the 2 remaining, but all you have to think about is which one is increasing more quickly, 3 to the x or 2 to the x. Should make sense that it's 3 to the x. Will be getting steeper, faster, so therefore we can identify it quite easily then. The blue one is 3 to the x, and the green one is 2 to the x. Okay, so imagine you could have points which follow these kinds of curves, right? And there are 2 types of curves effectively here. One's where x is the power and the number is the base, and one's where x is the base and a number is the power. And those are 2 very different kinds of curves. And you've been given 2 examples of each here for a total of 4 examples. Okay, so let's get into this concept then, exponential models. So the way we're going to prove or show that a set of data follows an exponential model, or follows a curve like we saw on the previous slide, is we need to make use of coding. And this, in this context, mathematical coding, it means coding like in the sense of a secret code, where you take an input and you turn it into something else. The only thing is it's not secret. There's a very clear mapping between what was our original data and what it then becomes. And this is a technique that's very useful, and we'll see why it's useful. But the concept of coding is very simple. It's taking a mathematical function. So, for instance, let's say, and I'm going to make up some values. Let's say here I've got some bivariate data. I'll make something up. I don't know if this is correlated or not. I'm doing it randomly, so it probably isn't. But let's say that's my set of data, and then I'm going to define a code. And the way you define a code is by convention, just capitalize each of the variables and then write them as a function of their respective lowercase version. So let's say I'm going to make up a code. Let's say big X equals 2x and capital Y equals, I don't know, y plus 4. Okay, and what that's going to give me is a new set of bivariate data, where in the first instance I've just doubled everything, and what did I say, y plus 4, so I get 11, 8, 3, 7. Okay, and you can get from the coded value, so if I just gave you this, the key part of the code is that it's not secret, and you can reverse it. So here we've got capital X, capital Y, and if I give if I give you these codes, you'll be able to get back to this data. So you can jump from the lowercase version to the uppercase version, from the uncoded to the coded and back again. Okay, so that's all coding data is. However, we're not going to do stuff like 2x or y plus 4. There's only one kind of code that we're going to be using, so that makes it quite simple. And that's going to be the following code. When we encode data, we are going to be doing, we're going to be using the function ln or log. Right. In fact, it doesn't particularly matter what base we use. In fact, because the base doesn't actually matter, let's just stick with log. And we can actually leave it ambiguous. But you're going to be using things like log x and log y. Okay, that's the kind of coding we're going to be using. Sometimes we might code both of them using the log, and sometimes we might only code one of them and leave the other one the same. For instance, you can have a code where one of the data variables doesn't even change. So that, for example, is a totally valid code. The x gets changed into the log of the x, and the y just stays the same. Okay, and then what you'd end up with here is you just get, for that specific code, the y's are the same, and here you're going to have, you know, log of 1, log of 3, whatever that is, and so on. Okay, cool. So that's coding. So let's see how we use it. So let's assume I've got a set of data, bivariate data, and it's not in the form y equals a plus bx. Okay, it's not in that form, so it's not linear. It doesn't look linear, but I think there's some sort of relationship. There are a couple of possibilities that we might want to check. Okay, ultimately there's an infinite amount of possible relationships, but if it's not a line, then another common one might be something exponential. So let's consider the following form. Let's say I suspect it might be in the form x squared or x cubed. So maybe my data, you know, looks like this if I think it's x squared or something like that. Or it could be x cubed or x to the 4. Or in general, rather than picking a power, let's just say it's in the form x to the power of n. And let's also say I'm actually not sure if I should multiply that by a number. You know, maybe it's 2x to the 5, maybe it's 7x to the 3. I really don't know. I just know it's roughly that form, and the specific numbers we can find later. So we'll generalize it a bit more, and we'll write it like this. Okay, and that's the standard form you'd write it in: y equals ax to the n. So now let's draw a little table, and let's consider. Okay, I'm going to code this. I'm going to code this as well. We need to figure out what the appropriate coding would be. So let's take log of both sides. So if I take log of both sides, I'm going to get log of y equals log of ax to the n, and that's the same as, well, it's a product, so I've got log of a plus log of x to the n using your log rules, and then using log rules one more time I get this n log x. Okay, yes, so this is a number, and that's a number. And if only this thing, log x, was just x, then this would actually be a line, wouldn't it? It would be a number plus a number times x. Unfortunately, it's not x, it's log x. So let's replace it. Let's call that thing here, let's call that capital X. So what we then end up with is a number plus n times capital X, which is a line, right? But we also need to consider the left-hand side. Remember, the left-hand side is log y, and really that should just be a single variable as well, capital Y. So now it works properly. We've got capital Y equals log A plus n log x. Okay, so here's the coding we're going to use. We're going to use the coding. Perhaps we didn't need to quite make this a table, but we're going to use the coding capital Y equals log of y, and capital X equals log of x, little x, and that coding gives me the following form: capital Y equals log of little a plus n times big X. Okay, and this thing, or really the whole thing, that's linear. Okay, it's y equals ax plus b, or mx plus c, however you remember it. It's a line, something times x plus a constant. So here's the thing. Here's the idea behind this. You're saying, okay, I assume my data is in this form. I'm then going to take all that data and replace it. I'm going to encode it by replacing all the y's with log y's and all the x's with log x's. And that coded data, I'm then going to plot that. And if it makes a line, then I know that what I started with was a correct assumption, that it was in fact this model. And if that coded data with the logs doesn't make a line, or doesn't make something close to a line, then I know, okay, my assumption was wrong, it's not in this form. Furthermore, if I do get a kind of a line shape, then I can figure out what a and n are. And how can I do that? Because n is the gradient and log of a is the y-intercept. So I can basically use a linear regression to find the values of n and a. Okay, so I do a linear regression, I'll get a gradient and a y-intercept, which on your calculator are shown as b and a respectively, and then I can find the values of a and n in this context. Just don't get confused that the little a here is not the a that your calculator shows. That a will be some number, and that number represents this whole thing, log of a. Okay, cool. So that's one possible coding. Let's look at the other one. I'll just clear some space. So another possibility is what we saw before, which was a number to the power of x, and we tend to use b to mean base. And again, we're going to multiply it by a constant. For whatever reason, we tend to use k. I don't know why we don't just use a, but it's just convention. So it's a constant times a constant to the power of x. So what coding should we use here? Actually, I'm just going to move that down slightly. So to figure out what coding is appropriate, let's try again. Let's log both sides. We get log of y equals log of k b to the x equals log of k plus log b to the x equals log of k plus x log b. So it's similar but slightly different. This time we're still going to replace log y with big Y, but over here that is already x and this is a number. Log b is just a number. So that little x, we're going to just keep that, just turn that into big X without changing it. And this one here, log k, we're just going to keep that as a number. Not keep it, sorry, that is a number. And now it's linear. It's y equals number plus number times x. So what that tells us is that we can, oh dear, let me clean this up slightly. We can code it as follows. So we're going to use the coding y equals log y, capital Y equals log of little y, and big X is just going to be the same as what little x was. So the little x won't be coded. I mean, it will in some sense, but it's just the code is to keep it the same. And that will give us the following form: y equals log of k plus log of b times big X. Okay, so again, you've got it in the form of something plus something x, and that's linear. So personally, I don't remember these encodings, and the reason why not is because you've just seen you can rederive them quite quickly. I've done it a bit slower, just for the sake of I have to explain it as I go. But if you've practiced this, you've done it at least once, you can see you can do it quite quick. You take the form, apply log to both sides, and just use a bit of logical deduction. What do I need to substitute to make it be a line? And then you'll have your coding, and then you'll know what form it ends up being in. Okay. So that's it. That's how we're going to do the coding. Okay. And then the concept itself is not too complicated. You can now do linear regression on stuff that actually isn't a line by encoding it into something that should be a line. Okay. And now again here, let's just clarify this actually. For the first case, the y-intercept is going to be log a. The gradient is n. And for the second version, the y-intercept has a value of log k, and the gradient is log of b. Cool. Okay, so hopefully that makes sense. Let's look at an example and you can try some questions. Okay, so we've got some bivariate data. Temperature versus the growth rate of some bacteria. The data are coded using the following change of variables: x equals t and y equals log of g. So already from that, from knowing that encoding, they've used different letters. Instead of little x and big X, they've gone from t to little x, and from g to or from log g to y. But this is the code, and so if you went back to the previous slide, you'd see it corresponds to one of them, doesn't it? In fact, in this case, it corresponds to the second one we did. So we already know that if you've used that specific coding where one of them stayed the same and the other one had a log applied, and you've got a regression line, as in it was actually a line or something close to a line, it must be in the following form. We must have the following form, that g is equal to k times b or to the power t, right? Before we had g as y and t as x, but it's basically in that form. Oh, in fact, yeah, you've got it here. They've given it to you. Right, but technically they didn't need to give that to you. So in a more advanced question, you might not actually have that. You should be able to deduce it's in this form based on the coding, assuming you've got a line. Okay, so then someone called Mika says the constant minus 0.2215 here in the regression line means that the colony is shrinking when the temperature is 0 degrees. Explain why Mika is wrong. Okay, so I mean, let's just first, before we talk about the actual correct answer, let's talk about the general mistake that's being made here. And the mistake is this person is looking at the coded data and making conclusions from the coded data without having referred back to the actual original data. So because when x is 0, well, what they've done is they've basically put x as being 0 and then got a negative value and then said, oh, what the output is negative, therefore at that value is negative. But the point is, when temperature is 0, that's T. So we have to actually consider the original equation here. Alternatively, we could just use the encoding. So let's rewrite that equation, but let's use the encoding. So what we've actually got is log of G is equal to the following, T. Okay, and you could rearrange that to turn it back into that form if you wanted to, but we don't actually have to. We can just work directly with this. Now let's substitute in a temperature of 0. So T of 0 is here. So at T equals 0, this implies that log of G is just going to be minus 0.2215, right? So then G must be equal to, and we're going to assume they're talking base 10 here now. So at this point the base does matter. Annoyingly, I won't get into the whole thing, but within A-level mathematics, log is base 10. So therefore G is equal to 10 to the power of minus 0.2215. And that comes out to be, check, roughly 0.6, which is a positive value. So that's the mistake they made. They put x as 0 rather than t as 0, and then they forgot that y is actually log of g, and g is the growth, not y. So don't forget to convert your coded linear equation back into the in terms of the uncoded data, which in this case is t and g. Cool. Okay, and then part B. Given that the data can be modelled by the following equation, yeah, we knew that already, where k and b are constants, yeah, we knew that. Find the values of k and b. Okay, so the general method for doing this is we're going to just start with the linear equation, and then having substituted in the code, so that's the line in red that we've got, and now we're just going to rearrange it. So we're going to make g the subject. So I'm going to do that by doing 10 to the power of both sides. So 10 to the log g gives me g, and 10 to the power of the right hand side gives me this. And then I can split that apart, because if I've got a power that's a sum, then I can separate that into the product of two powers. So we've got that, which is just a number, times 10 to the 0.0792 t. And then I can go one step further, and this I would do a new line of working, but I'm running out of space. So this t multiplying the power, as you know from your power rules, I can actually just raise the whole thing to the power t, and it means the same thing. So let's do that. So I've got this, and we're in the form, right? This thing, 10 to the minus 0.2215, that's my k, and this thing, 10 to the 0.0792, that's my b. And now I've written it as g equals k times b to the t. You'd obviously want to use your calculator, find out what those values actually are. I don't think I have it in front of me, but it doesn't matter. You've got the method there. Okay, cool. All right, that's it. So let's try some questions yourself, or I'll let you try some questions. Okay, so we've got 4 parts. It's only 1 question per slide, and I'll just let you work your way through those. Pause the video now, and you can try the first one. And then you've got question 2. Give that one a go. Make sure you're checking your answers in the back for the explanation questions. And give this one a go. And finally, have a go at this one. Not too difficult, B and C. quick explanation. Cool, great. Hopefully you've had a go at all those.